Disclaimer: this video is not intended for someone to copy the answer and put it into Isaac Physics. It is intended to guide the confused problem solver through the process of these interesting questions. Hanging on a non-uniform bar. I'll give you the tools to solve this question in this video. It's on Isaac Physics and you can see it on the screen right now, and I'll leave a link in the description. So as I mentioned, I'll give you the tools to solve it. At each section of the video, I'm going to format it in such a way that I'll give you some time to pause and try and calculate it yourself. So I'll call out these sections and the video will keep going. And I highly recommend that first of all, you try and solve this question by yourself. And if you can't, follow along with this video, and at each section try and pause and go through with the calculation yourself. Okay, so without further ado, first of all, with these sort of questions, you need to draw a diagram. So I've drawn a diagram and I've written down the aim. So the aim is to find the distance of the center of mass to the closest edge of the rod. So we have our rod here and the strings and the wall. So the strings each have a tension force in it, T1 and T2, and these are angled to the vertical lines running up from the ends of the rod. Also, the rod has a mass, therefore it has a weight. The rod is 1 meter long. It has an unknown distance across center of mass. So I've written the distances from each of the edges. I've labeled them as X and Y. So X being the shorter one, Y being the longer one, but only time will tell which one is actually the longer one, because I'm just making a guess just to simplify it now. So now that we've got this diagram, I'd encourage you to either copy this or make your own one. And with that aim in mind, try and pause and calculate and come up with the answer on your own. And if you get stuck, join me in the next part of the video. Okay, so now you must have given it a go and tried to solve this question. The next step that I would take personally with any of the problems of this sort, any problem which really involves forces, is to resolve. So resolve in the vertical direction, in the horizontal direction, whichever directions are relevant. In inclined plane problems, you'll usually find it easier to resolve perpendicular to the plane and parallel to the plane, but in most problems, and indeed in this one, it's easier just to resolve up and down, left and right. So upwards and sideways. Okay, so let's first resolve upwards, and we've got the vertical component of each force. So T2 cos 53.1, so that's that force, that's that component of the force, plus T1 cos 36.9, that's that component, minus mg equals 0, because this is F equals ma, and in this case the rod's not really moving upwards or downwards or left or right, so our acceleration is 0, and therefore we can write in this format. So we can also make that equal to mg and manipulate it later, but for the moment I'm just gonna let it for the moment I'm just gonna leave it alone, because it's important to resolve in both directions to avoid getting carried away with manipulating one direction when actually the other direction may be useful as well. So let's do this. If I'm resolving right, T1, the horizontal component of that, is going to be quite important. So let's do that first. T1 cos 36.9 minus T2, T1 sine, sorry. Sine means that component. T1 times sine means the opposite. and T2 is the opposite direction, so we're going to take it away. So minus T2 sine 53.1 equals 0 again because it's not moving in the left or right direction. So now actually this turns out to be more useful. So we got T1 sine 53.9 equals T2 sine 53.1. T2 equals T1 sine 53.9 divided by, no, where did I get 53.9 from? Sorry. T1 sine 36.9 divided by sine 53.1. So now we've got T2 in terms of T1 and sine 36.9, sine 53.1, which are just numbers. Okay, so now I'd highly encourage you to pause and calculate, try and figure out the next stage, and that will just involve trying to get these x and y distances involved. And once you get that, you'll be able to get the values of those distances. So how are you going to get this force involved with the distance? That's what we have to figure out. So I presume you've had a think over it. Either you've got it or not, but the way to involve distances with forces is moments. So we're going to take moments around the most convenient point, which seems to be the center of mass, because we can get both these involved and not have to consider this weight. And that really simplifies our calculations. So I'm going to take moments about the center point, center of mass, sorry, and yeah, that's going to be x times, so with moments we only consider forces that are perpendicular to the thing that's turning. So the rod is the thing that's turning, so forces perpendicular to that are the weight, but because the weight is acting at the center point, we don't have to worry about that. We only have to worry about the vertical component of the tension on both of these sides. So x times T2 cos 53.1, and we have that equal to y times T1 cos 36.9. Okay, so now we've got this. Let's try and figure out what we can do with this. Well, we have this handy result round top, so we're going to use that. X times T1 sine 36.9 over sine 53.1, and then multiply that by cos 53.1, and that equals y times T1 cos 36.9. Alright, now we can just go ahead and try and simplify this down. So we can do this. X times T1 sine 36.9 cos 53.1 divided by sine 53.1, and that's y times T1 cos 36.9. So now it's time to cancel out things that are in common with both sides. So let us have a look at this. So what's in common? We've got T1 on both sides, so we can cancel those out. and well, that's pretty much all that's in common. So now we can get y on its own, because that seems the easier side to get on its own. So we can do that by dividing by cos 36.9. So x times sine 36.9 cos 53.1 over sine 53.1 times cos 36.9. So now we have x directly related to y, and we have y directly in terms of x. Sorry if that was confusing. Now the next stage is to try and get this to become an equation in x. So we can try and figure out a way to solve for x, and then we can get y, and then we can find out which is the closer edge. So we're right near the end, and we can use this diagram in some sort of way to help us with that. So I'd encourage you to pause and calculate. This is an easy one, but a hard one at the same time. So in order to relate this equation in terms of x only, so put this equation in terms of x only, you need to take advantage of a simple fact which I missed during the first part of my solving the problem, and it really nagged me until I finally got it. So the simplest relation here we have is x plus y equals 1. And that's a relation we can use to finalize our answer. So if x plus y equals 1, then we can put our equation in terms of that. So x times sine 36.9 cos 53.1 divided by sine 53.1 cos 36.9. So this equation implies that y equals 1 minus x. So this equals 1 minus x. So now it's just plain up solving equations. So it's very easy, straight up. So we just factorize by bringing x over to this side. So we have x plus x times, so I'm going to simplify this down by just writing it in terms of tan and cot, which is 1 over tan. But actually I'm just going to write in terms of tan. That would be the easiest way. So x times, because we have sine 36.9 and cos 36.9, we have sine 36.9 over cos 36.9 times cos 53.1 over sine 53.1 equals 1. Now I'm going to do this. Simplify even more. X plus x tan 36.9 times 1 over tan 53.1 equals to 1. Now, what do we do next? Factorize 1 plus tan 36.9 over tan 53.1 equals to 1. Let me just do this even more. Tan 53.1, just simplify it more so we can easily put into our calculator. Over tan 53.1. Now when we divide both sides by this amount, it's the equivalent to multiplying by tan 53.1 over tan 53.1 plus tan 36.9, and because we have 1 on that side, it just becomes the reciprocal. So we flip the fraction upside down, equals tan 53.1 over tan 53.1 plus tan 36.9. So now all we have to do is put it into our calculator and find out whether this is the shorter side or not. So tan 53.1, make sure your calculator is set to degrees, over tan 53.1 plus tan 36.9. And we get 0.639. So we can obviously tell that this is not the longer side. This is the longer side, sorry. So the longer distance, and that's not what we want. We want the shorter side, right? So that means if x is the longer side, then y must be the shorter side. So 1 minus 0.639, so 1 minus x equals y, which is the shorter side. 1 minus that equals 0.3605, and to 3 significant figures, that's 0.361. There you go. Pretty easy, right? With these sort of problems, it's just a methodical way of solving the question. And initially it might seem tough, but there's always a simple fact which you have to look for that might simplify the problem. Sometimes it's actually just all grinding it out, doing the hard way. But in this case, there turns out to be a simple fact that simplifies our solution and really helps us out. I mean, we could have even got carried away with resolving upwards and figuring out things in terms of mg and stuff we didn't know. But by looking at all the pieces of evidence that we have and trying to figure out a simple relationship, it has led us to an easy and nice concise solution. 0.361 meters is the closest distance.